Hello everybody, myself Jyoti and today we will discuss about the nuclear reactor. What is a nuclear reactor? A system in which the fissionable and non-fissionable materials are arranged so that fission chain reaction can proceed in a controlled manner. So we know that if you have to, when we have already studied the uranium-235 fission chain reaction. So we know that if we do not control that reaction, then the reaction can become uncontrolled. We don't want uncontrolled chain reaction. So when we a system where we can have a fission chain reaction in a controlled manner, that is called as nuclear reactor. So what are the special features of nuclear reactor? We will talk about neutron energies, then the fuel moderator assembly, the moderator, the coolant, and what is the purpose of a nuclear reactor. Neutron energies. So first we will have to decide neutron energies at which most of the fissions occur: fast, intermediate, or thermal. So when we talk about uranium-238, it can cause fission reaction with the help of fast neutrons. But when we talk about uranium-235, for uranium-235, nuclear fission reaction takes place with thermal neutrons. So you have to decide neutron energy, whether you need fast neutron, intermediate neutron, or thermal neutron. Then the fuel, so natural uranium, enriched uranium, plutonium 239 or uranium 239, generally these are used as the fuel. Now, what is the difference between natural and enriched uranium? So enriched uranium is a type of uranium in which percentage composition of uranium-235 has been increased through a process of isotope separation. So when we talk about natural uranium has 99% uranium-238 and less than 0.7% uranium-235. Generally, we go for uranium-235 nuclear fission, right? So here the percentage of uranium-235 it is very less. Now low enriched uranium, it has typically less than 20% of uranium-235, or typically you can say 3 to 5% of uranium-235, and highly enriched uranium, it has 20 to 85% of uranium-235. Now fuel and moderator assembly. So this assembly of fuel and moderator, it is heterogeneous or homogeneous. Heterogeneous in the sense, suppose I have uranium, which is fuel, and plutonium, and they are arranged in small portions and are isolated from each other by moderator. So fuel may we are using uranium and plutonium and they are separated by moderator material. Then it is called as heterogeneous. At times what happens, uranium, it is mixed with the moderator, like we mix the fine powder of uranium or one of its salts in either ordinary or heavy water, then that is the homogeneous kind of fuel moderator assembly. Now the moderators which are generally used, they may be graphite, water, heavy water, beryllium or beryllium oxide. And the coolant, so we need a coolant also because large amount of heat will be evolved. So the coolant which are generally used, it is air, then carbon dioxide, helium, water or other liquid, and liquid metal. What is the purpose of nuclear reactor? Nuclear reactor, it is used in research, it is used for the production of fissile material, and it is also used for generation of power. So what is a nuclear reactor? It is the source of the products of the fission process, namely energy, neutrons and radioactive isotopes. And here, as a source of neutrons, a nuclear reactor can provide a large number of neutrons per unit time with a wide range of energies. So if you take the example of uranium-235, it captures a neutron, thermal neutron, it produces uranium-236, which is a compound nucleus. It gives fission fragments which are barium and krypton, and along with it 3 neutrons are emitted. So if you consider chain reaction, from 3 you will get 9, from 9 you will get 27, and so on. So in a nuclear reactor we get a large number of neutrons per unit time, and with a wide range of energies. Now, how the power level of a nuclear reactor is controlled, because we have to control it, otherwise the chain reaction itself, it is uncontrollable. So the power level at which a reactor operates is proportional to number of fissions occurring per unit time, because for in each fission you are going to get 3 neutrons and approximately 200 MeV of energy in case of uranium-235. So the power level at which a reactor operates is proportional to number of fissions, and in turn you can say number of neutrons in the reactor. So if you have to if you want to control power level of the reactant, you will have to control the number of neutrons in it. And a common method of doing this is to introduce neutron absorbing material, which is generally in the form of steel or a cadmium rod containing boron, and to adjust the position of this rod in the core. This essentially changes the value of K in the desired direction. So what is K? That it is a reproduction factor, so which we have already studied in the 4-factor formula. So if the number of neutrons are increasing rapidly and you want lesser number of neutrons, because otherwise it will become uncontrollable reaction, you will have to insert a neutron absorbing material inside the nuclear reactor. And as the reactor continues in operation, the fissionable material is used up, because our fissionable material, suppose it is uranium-235 and it has been utilized in the chain reaction, so it will be used up. And if you want to keep the power level constant, the control rods containing neutron absorbing materials should be moved out of the reactor at a suitable rate. It's not like that you have inserted inside and then all the neutrons are absorbed, because we need neutrons for a further chain reaction as well. So now why the neutrons generated is more as compared to ones which are lost. So if we talk about the neutron we know that it is unstable and it has a decay half-life of the 11 minutes. But this is not going to have any effect on the operation of a nuclear reactor, because when we are talking about the fission reaction, it is taking place very rapidly. And this time interval of producing of neutrons through a fission reaction, which is called as the time of neutron generation, it is usually smaller than 10 raised to minus 3 seconds. So there is, and if you compare the half-life, it is 11 minutes. So you can imagine that only negligible fraction of neutron produced are lost and not many, because half-life of 11 minutes, it is far more as compared to 10 raised to minus 3 seconds. It is seen that pure natural uranium cannot support a chain reaction. However, natural uranium which is suitably arranged with graphite or heavy water can support a chain reaction. And the graphite or heavy water, it also acts as a moderator to slow down highly energetic neutrons reduced in the fission of uranium, because whenever nuclear fission reaction will take place, it will produce fast neutrons, and these fast neutrons, if they are captured by uranium-235, they will not going to cause any nuclear fission. So we will have to use moderator which will slow down these energetic neutrons, which will in turn become thermal neutrons and cause further fission of uranium. The neutrons get scattered at reduced energies after colliding with moderator, and with a sufficient amount of moderator in the reactor, the neutrons are reduced to thermal energies and thus a chain reaction can be produced. So this is all about a nuclear reactor. Thank you so much.